Hello everyone. The title of this video is Finding the Zeros of Polynomial Functions. Alright, so in this video I'm going to be taking examples directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text, section 5.5 called Zeros of Polynomial Functions, and I'm under the heading Finding the Zeros of Polynomial Functions. Now I am assuming that you know what the rational zero theorem is. I put a previous video on that, and it also shows up previously in this reading in this section, and how to use the rational zero theorem. Right. And each example I'm going to be doing is taken either from the examples in this text or the try it problems or one of the exercises at the end of the section related to this objective. Now, as I said, I'm assuming you know the rational zero theorem and how it helps us make a list of possible rational zeros for a polynomial function that has integer coefficients. Right. And then there's this little how-to here. And I'm going to be following pretty much these same steps for each of the examples I'm going to show you today. So given a polynomial function f, use synthetic division to find its zeros. And I also did this in my previous video on the rational zero theorem. But first we're going to use the rational zero theorem to list all possible rational zeros of the function. Then I'm going to use synthetic division to evaluate a given possible zero. Right. If the remainder is 0, then that number is a 0. Right. The number I plugged in is a 0 of the function. And then, well, I'm not going to keep doing that. If I find a 0, I'm going to use that 0 to help me factor the polynomial, and then we can repeat step 2. Alright, so let me just get into the examples. So we're asked in the examples I've first written, we're asked to find the real zeros of a function, the real solutions of an equation, which, solving this equation here, right, I have, solve x cubed minus 3x squared minus 10x plus 24 equals 0. This is the same thing as asking you to find the zeros of this polynomial function. Say f of x equals this polynomial, right, x cubed minus 3x squared minus 10x plus 24. Right. If I say here's a polynomial function, find the zeros, that's exactly the same as solving this equation, right? Setting the polynomial equal to 0. Right. Now, notice that every coefficient, right, all the coefficients are integers. 1, negative 3, negative 10, positive 24, right? And if that's the case, right, if all the coefficients are integers, then we can apply the rational zero theorem. Which for the rest of the video I'm just going to abbreviate the rational zero theorem with RZT. Right. Now remember what the rational zero theorem states, right, RZT. States that, if a polynomial function with integer coefficients, which this is, if it has any rational zeros, they're going to look like the following. Right, so by the rational zero theorem, any rational zero or any rational solution of this equation will look like the following. X equals, and then some rational number, fraction, ratio of two integers, where the numerator has got to be a factor, some factor of the constant term, which is positive 24 here. Right, the constant term. And the denominator has to be some factor of 1, right, the lead coefficient. All right, so if we make a little, I'm going to do another fraction here. And I'll make a list of, I'll just write out what are the possible numerators. Well, factors of 24 are positive or negative 1, positive or negative 2, positive or negative 3, positive or negative 4, positive or negative 6, positive or negative 8. Sorry, this is going into here. Positive or negative 12, and positive or negative 24. Right, and then the denominator is going to be 1. I already used the negatives up top. I don't need to use them again. So from this, we should be able to make a list of possible rational zeros for this polynomial. Now notice I use the word possible. Remember, the rational zero theorem doesn't guarantee that you're going to find a rational zero. All the rational zero theorem states is that if a polynomial has a rational zero, it's got to look a certain way. That's all the rational zero theorem states. So we can use this to make a list of possible rational zeros. And really, since the denominator is always 1, it's just these factors of 24. So positive 1 or negative 1, positive 2 or negative 2, positive 3 or negative 3, positive 4 or negative 4, positive 6 or negative 6, positive 8 or negative 8, positive 12 or negative 12, and finally positive or negative 24. All right. So these 16 numbers are the possible rational solutions to this equation. Now it's only a degree 3 polynomial, so at most it's going to have 3 zeros. So there's no way all of these are working. All right. Again, this is just possible rational solutions, rational zeros. All right, so then we start checking them. All right. Check for zeros from this list. Now you can do it with synthetic division or just plug them in. Now synthetic division is nice because once you find a zero, you can then easily factor the polynomial. So I'm going to set up my little synthetic division cross here. Again, if you want to use the symbol they use, fine, but I like doing it this way. And you probably saw in my last video on the rational zero theorem why I like doing it this way, because you can just extend it to plug in more numbers. So up top I have the coefficients of our polynomial. We have 1x cubed, negative 3x squared, negative 10x, and then positive 24 is the constant term. And then, it's basically like an input-output table. Right, here I'm going to plug in a number. Say I plug in 1, right, the first number on my list. And then perform synthetic division. Remember, the first coefficient drops down, then you multiply, add, multiply, add, multiply, add. I'm just going to speak it out, because I'm going to be doing this a bunch of times. I don't want to write all these numbers up top. 1 times 1 is 1, plus negative 3 is negative 2. 1 times negative 2 is negative 2, plus negative 10 is negative 12. And then 1 times negative 12 is negative 12, plus 24 is positive 12, right? So what this is telling me is that f of 1 is 12. Or if I were to plug in 1 for x, I'd get 12 equals 0, which is false, right? So this is not a solution, right? X equals 1 is not a solution, not a solution, not a 0. And then I just make this longer, extend this. Now you can plug in -1, but I already see that 2 is going to work. I mean, these aren't that big. These numbers aren't that large. So you could plug in -1 if you want, but I'm going to plug in 2 next, all right? Because I already see that it works. And watch it work. All right, so drop the 1, then multiply, add, you get -1, then -2, plus -10 is -12, right? And then 2 times -12 is -24, plus 24 is 0. So we're seeing from this that f of 2 is 0, right? Or if I were to plug 2 in for x, you'd have 0 equals 0. This is a solution. Yes. Okay. Now, I brought this up in the last video as well on the rational zero theorem. I'll say once you find a 0, I mean, you can keep going with the list. Keep going, plug in -1, plug in -2, plug in 3, plug in -3, plug in 4, plug in -4, and so on. And you can keep going with the list to try to find other rational zeros if you wish. But let me show you, I feel, a faster way of continuing. So once you find a 0, factor the polynomial. So watch this. Right? So we had what? We had f of x. We called this function, this polynomial f of x was x cubed minus 3x squared minus 10x plus 24. But now I should be able to factor it using this line right here. Remember, if 2 was what I plugged in, that means my divisor was x minus 2, right? If 2 is a 0, then x minus 2 is a factor. So I can write this as x minus 2 times, and then these numbers in between the bars here, these are the coefficients of the quotient, which would be a degree 2 in this case, 2, 1, 0, right? It's in descending order. So it's 1x squared minus 1x minus 12. So we know that 2 is a 0. And now I just move over and let's find the zeros of this quadratic polynomial, which is much easier, right, than a degree 3. Now you can use the quadratic formula, right? It's a quadratic with a equals 1, b equals -1, and c equals -12. You can use the quadratic formula to find the zeros, or factor it, which, this is factorable. X squared minus x minus 12 would factor to x minus 4 times x plus 3. Alright, and then you can see other factors and then very easily see all the zeros, right? So the zeros of this function are x equals 2, right? Because that makes the factor x minus 2 equals 0. And then the numbers that make these factors 0 are positive 4 and negative 3. And there you go. And these are real numbers, right? These are real numbers, all three of these. So that means, all that means is that the graph of this function, if you were to graph this polynomial function, it would actually hit the x-axis at 2, 4, and -3. And let's see that happening. All right, let's see that happening. So I'm going to go to that free online graphing calculator website, desmos.com, and enter that polynomial function. We had f of x equals, and our polynomial was this degree 3, x cubed minus 3x squared minus 10x, and then plus 24, 4. And look at the x-intercepts. See, there's -3, 0, 2, 0, 4, 0. The x-intercepts, right, the real number zeros are 2, 4, and -3, just like I wrote here. Right, x equals 2, 4, -3. And so those would be the solutions also of this equation. When is the polynomial equal to 0? And you can check it, right? Plug in these numbers. If you plug in 2, that's 8, minus 12 is -4, minus 20 is negative 24, plus 24 is 0. That works. If I plug in 4, 4 cubed is 64. 3 times 16 is 48. 64 minus 48 be 16. Then minus 40 is negative 24, plus 24 is 0. And then plug in negative 3, right? Negative 3 cubed is negative 27. You have minus another 27 is negative 54. Plus 30 plus 24 is positive 54. Negative 54 plus 54 is 0. All three of these work in that equation. Right. But this is the procedure I'm going to be going through for all of these. We're going to see some polynomial, equal to 0. Right. So basically, we're finding the zeros of some polynomial function, and just make sure all the coefficients are integers. Right. If one of them is a fraction or something, just multiply through by the LCD. Make all the coefficients integers so we can apply the rational zero theorem. Right. Then we apply the rational zero theorem to make a list of all the possible rational zeros the function could have, and then we check that list for zeros, and then once you find a zero, use it to factor. And you should eventually be able to factor these polynomials down to degree 1 factors and degree 2 factors, linear and quadratic. Linears, easy to find zeros of those. The quadratics, you can try factoring further or use the quadratic formula to find the zeros of those. And that's what I'm doing for the rest of this. All right, so again, another equation. Now we're asked to solve this equation here. We have x cubed plus 2x squared minus 9x minus 18 equals 0. Again, solving this equation means the same thing as finding the zeros of this polynomial. F of x equals, this cubic polynomial here, x cubed plus 2x squared minus 9x minus 18. Now, this is one of those nice ones where I can actually see how to factor this polynomial without using the rational zero theorem. You can factor this by grouping. All right, this is x cubed plus 2x squared in the first group, and then plus and then negative 9x minus 18 in the second group. First group, you pull out x squared, then you have times x plus 2. Second group, I'd factor out negative 9. I hope you remember how to factor by grouping. And then you have x plus 2 come out, and then x squared minus 9 left over. And that x squared minus 9, that's a difference of squares. That factors to x minus 3 times x plus 3. All right, so if you can see how to factor it right away by grouping or some other method you've learned, do that. So I can very easily see that the zeros of this function, or the solutions of this equation, are x equals negative 2. Right, that makes x plus 2 0. X equals positive 3, and x equals negative 3. And all three of these numbers are real. Right, these are all real solutions, and that's all they're asking us for, right? These are real numbers. And there you go. All right, and if you were to look at the graph of this function, it would cross the x-axis at negative 2, 3, and negative 3. All right, now suppose you didn't see that. Say you forgot how to group, or at least you forgot how to even try factoring by grouping. Well, all the coefficients of this polynomial are integers, so we can apply that rational zeros theorem, RZT. By the rational zeros theorem, any rational zero of this polynomial is going to take on the following form. The numerator has got to be some factor of the constant term, right? Some factor of negative 18, and the denominator has got to be some factor of 1, right? The lead coefficient. So basically, when I talk about the list of possible rational zeros, it's just the factors, numbers that go into 18 evenly, because the denominator is always going to be 1. Right? So positive or negative 1, positive or negative 2, positive or negative 3, positive or negative 6, positive or negative 9, and positive or negative 18. Right, here's a list of your possible rational zeros. Notice that the ones I found all over here, -2, +3, these are all rational, and they're on the list. +2, +3, and -3, or sorry, -2, +3, and -3. All these are rational, and they're on this list. And then we start checking using synthetic division. So up top, the coefficients of my polynomial, 1x cubed, +2x squared, -9x to the first, -18. And then again, suppose you didn't see what the zeros were already, and you start checking, how about 1? 1's on this list, so I drop the 1, and 1 times 1 is 1, plus 2 is 3, and then 3 plus -9 is -6, and then -6 plus -18 is, -24, so nope, x equals 1 doesn't work. You'd have -24 equals 0, that's not true. Then how about -1? Drop the 1. -1 plus 2 is 1. -1 plus -9 is -10. And then 10 plus -18 is -8. So once again, that's not a solution. That's not, -1 is not a 0. And then you keep going. Hey, how about +2? Right, and drop the 1. 2 plus 2 is 4. 8 plus -9 is -1. And then -2 plus -18 is -20. Nope. +2 is not a 0. And then look at this, right? Now -2, if everything I did over here is correct, -2 should work. I should end up with a 0 here. So drop the 1. -2 plus 2 is 0. 0 plus -9 is -9. And then -2 times -9 is +18 plus -18 is 0. Hooray. And then as I said earlier, once you find a 0, you should be able to factor this polynomial, right? F of x, instead of being x cubed plus 2x squared minus 9x minus 18, should be, -2 is the 0. So that means my divisor was x plus 2. X plus 2 is a factor. And then these numbers here, right, give me the coefficients of the quotient, which would be a degree 2, 1x squared plus 0x, which I don't need to write, and then minus 9. And then I can factor this even further. Basically, it just turns out to be like this now, right? Because x plus 2, that's as factored as that goes. X squared minus 9 factors to x minus 3 times x plus 3. Right? And then I can find all the zeros. So, once you find one 0 on the list, you should be able to then factor the polynomial, and then look at the other factor, look at the quotient, and see if you can factor that any further. Right? And once you get down to degree 1 factors and degree 2 factors, you should be able to find the zeros pretty easily. Right. And once again, let me just check it out, just a triple check, I guess, because I've kind of double checked. This is twice. Let's take a look at the graph of that function. So we were given this polynomial function here. It was x to the third plus 2x squared minus 9x minus 18. And look at, they have the x-intercepts highlighted. See the 3 zeros, -3, +2, or sorry, -2, yeah, and +3. The exact same numbers I had written out as well. Those are your real numbers. If you're on the x-axis, those are real numbers. These are your real number zeros. Okay, let's keep doing this. It's the same stuff every time. All right, so next example. All right, now again, we're looking at the basically we're finding the zeros of this polynomial function. All right, it's everything equals 0. Some polynomial x cubed minus 3x squared minus 25x plus 75. When is this equal to 0? And once again, I see that this can be factored by grouping. You could pull out the x squared from the first two terms, leaving you with x minus 3. And then from the next two terms, you pull out negative 25. And then you'd have again the factor x minus 3. And then, x minus 3 is common to both of these. And the other factor left over would be x squared minus 25. And there's another difference of squares, x squared minus 5 squared. So this factors to x minus 3 times x minus 5 times x plus 5, right? And so I can immediately tell you the zeros now. X equals positive 3, positive 5, and negative 5. All right, well, again, so two examples in a row here. I've had a polynomial up that could be factored by grouping. But that is not always the case, right? That first example I had up could not be factored with the grouping method. So again, if you don't see that, don't worry about it. You can always do the same procedure I've been doing. So I notice, hey, all these coefficients are integers. All right, so by the rational zero theorem, if this has any rational zeros, they're going to look like this. The numerator's got to be some factor of 75, and the denominator's got to be some factor of the lead coefficient, which is 1. So again, the list of possible rational zeros then is just the factors of 75, the numbers, because the denominator is going to be 1 again. So positive or negative 1, positive or negative 3, positive or negative 5, positive or negative 15, right, positive or negative 25, and finally positive or negative 75. Right? And there's, if this polynomial, this equation has any rational solutions, rational number zeros, they got to be on this list. And look, we know what they are, and they are, right? 3, 5, and negative 5 are on this list, and those are rational zeros. But again, say you don't know this. Say you don't want to cover up my hand here. Then we start checking. And I'm going to check with synthetic division. So up top here, the coefficients of the polynomial, 1x cubed, negative 3x squared, negative 25x to the first, positive 75 for the constant term. Now if I were to plug in 1, now I'm just going to do 1 and then I'll just go to one of the numbers that we know works. Drop the 1, 1 times 1 is 1, minus 3 is negative 2, then negative 2 minus 25, negative 27, then negative 27 plus 75, or 75 minus 27 would be 48. Positive 48, so no on that. If I were to plug in 1, you'd get, 48 equals 0. That's not true. And if you were, plug in some other stuff if you wish. At this time I would probably get to 3 before I got to 5, but let's see what happens when I plug in 5, just to get some different factoring. So I drop the 1, then, 5 minus 3 is 2. 10 minus 25 is negative 15, and then 5 times negative 15 is negative 75 plus 75 is 0. Right? So yes, I found a 0. 5 is a 0. So I should be able to factor the polynomial. Right? It's equal to x minus 5 then, times, and then these numbers here give me the other factor, the quotient, which would be 1x squared plus 2x minus 15. And then, like I said before, this is a quadratic, so you could use the quadratic formula to find the zeros, or try factoring. Right? This actually factors further. So we have x minus 5, and then x squared plus 2x minus 15 would factor to x plus 5 times x minus 3. And it's the exact same factors as I got up here when I did grouping, right? Just in a different order. But all the zeros would be the same, right? X equals positive 3, negative 5, positive 5. Those all make it 0. And those are real numbers as well, right? Every rational number is a real number. So these should also be showing up, when you graph. The graph should be crossing the x-axis at these values. And let's see that happening. Do a triple check. All right. So I instead of putting in f of x, nice thing about Desmos is if you have a function that depends on just x, you can just type in the expression and it assumes it's a function and puts the graph in. So I can just type in the polynomial. We have x cubed minus 3x squared minus 25x and then plus 75. All right. And see the intercepts, x-intercepts, these 3 points here, -5, +3, +5. Exactly the same 3 numbers, the same 3 zeros, same 3 solutions I wrote out on paper here. All right, let's do it again. Same procedure every time. Right? Now this one, this polynomial, again, we're just finding the zeros, what makes this 0, right? If there wasn't 0 on the other side, I'd subtract it, make 0 on the other side, and then we go through the same process. Now this one, you can't factor by grouping, or at least in the same sense that we've been doing the last couple of examples. So this one I kind of have to start off noticing, hey, all the coefficients are integers, great, so I can apply the rational zero theorem. And according to the rational zero theorem, if this has any rational zeros, it's going to look like the following, take the following form. X equals, the numerator's got to be some factor of the constant term, right, so some factor of -6, and the denominator's got to be some factor of the lead coefficient, which is 2. Now the possible numerators could be positive or -1, positive or -2, positive or -3, and positive or -6, right? Those are all the factors of 6. And then since I use the negatives up here, I don't need them down here. The factors of 2 are 1 and 2. So when I go to make this list, right, of possible rational solutions, possible rational zeros, I just take every combination of these. So plus or minus 1 over 1, so positive or -1, plus or minus 1 over 2, right? So positive or -1/2. Then move over to the 2's, plus or minus 2 over 1, so positive or -2. Then 2 over 2 I already have, that's 1, so I don't need to write that again. Then move over to the 3 over 1, plus or minus, right? Positive or -3. 3 over 2 I don't have, right? So positive or -3/2 or 1.5, 1.5. And then move over to the 6, positive or -6. Positive or negative, 6 over 2 I already have, that's 3. So I don't need to write that again. And there you go. So these 12 numbers, there are 12 numbers here that are possible rational zeros. Doesn't mean that they are, right? You got to plug them in, you got to check. And that's what we'll do next. So let's start checking these. Now if you want to use a calculator to make it faster, fine, or look at the graph of this polynomial function, make it faster, that's cool. But I'm going to do this one fully by hand here just to show you how I would do it by hand. So we have 2x cubed, 1x squared, -7x to the first, and then -6 for the constant term. So let's try 1 first. How about that? Right. So 2. 2 plus 1 is 3. 3 minus 7, -4. And then -4 minus 6 is -10. So not 1. How about -1? So drop the 2. Right. -2 plus 1, -1. 1 minus 7, -6. And then 6 minus 6, hey, 0. So -1, that's a solution to this equation. That is a 0 of that polynomial function. So that means we can factor this thing. So instead of 2x cubed plus x squared minus 7x minus 6, I can write it as x plus 1 times, and then this gives me 2x squared minus x minus 6. And now this here, it's a quadratic. You can use the quadratic formula to find the zeros of this factor, or you can try factoring it. This is factorable. 2 times negative 6 is negative 12. And factors of negative 12 that add up to negative 1 are negative 4 and positive 3. So yeah, this would factor. You have x plus 1, and this would factor. You'd have to have 2x in one of them, x in the other. And yeah, I would need a minus 2 over here to give me the minus 4x, and then plus 3 here to give me plus 3x for the minus 1x. And then 3 times negative 2 gives me the negative 6. So, now that it's nice and completely factored, I can easily state the zeros, right? Now, we already saw negative 1 works, right? That makes x plus 1 0. How about 2x plus 3? You know, when is that 0? When x is negative 3 halves. Which is rational, and notice that it is on the list. Right? Any rational zeros should be on this list of possible rational zeros that I made earlier. And then x minus 2 is a factor, so x equals 2 is a 0. And again, we have a rational 0, and notice that 2 was on my list. Right? Any rational 0 should be on that list of possible rational zeros. If you find a 0 that's rational, that's not on the list you made, then you did something wrong. And these are all real as well, right? Any rational number is also a real 0. And let's double check this. I'm going to plot the graph of this polynomial function, right, the polynomial they gave us, and see that it equals 0, or it crosses the x-axis at negative 1, negative 1.5, and positive 2. All right, so the polynomial here that we're finding the zeros of is 2x cubed plus x squared minus 7x minus 6. And you see the 3 x-intercepts, the 3 real zeros. Negative 1.5, that's your negative 3 halves. Negative 1 and positive 2. Exactly what I wrote on paper right here. Great. Let's do that again. Got several of these left. Just want to make sure you're seeing enough of it to get the hang of it. So again, I'm finding the zeros of this polynomial function here. You know, when is it equal to 0? All the coefficients are integers, right? No fractions, no decimals, no irrationals. So since all the coefficients are integers, I can apply the rational zero theorem, RZT. And any rational 0 of this polynomial, the numerator's got to be a factor of negative 6, and the denominator has to be a factor of 3. Right, now the possible numerators, right, all the factors of negative 6 are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And then the only factors of 3 are 1 and 3. Alright, then I take every combination of these and I can make this list of possible rational zeros. So positive or negative 1, positive or negative 1/3, positive or negative 2, and positive or negative 2/3. Positive or negative 3, now 3/3 is 1, I don't need to write that again. And then positive or negative 6, and 6/3 is 2, don't need to write that again. So here you go, another list with 12 numbers on it. And you know, some of these 12 may actually satisfy the equation, and that's what we're going to check. So now let's start checking the numbers from this list, and like I've been doing, right, using synthetic division. Again, if you have a calculator, you want to go to Desmos, check it out. Cool. All right, I'm just going to do it by hand right now. 3x cubed, negative 1x squared, negative 11x to the first, and negative 6. Start with 1. All right, 3 minus 1 is 2. 2 minus 11 is negative 9. Negative 9 minus 6, negative 15, right? So not that one. Let's make these longer. How about negative 1? Negative 3 minus 1 is negative 4. Positive 4 minus 11, negative 7. And then positive 7 minus 6 is 1. So no again. But here's something I'm noticing. From these two lines, see how when I plug in 1, the output's negative. When I plug in negative 1, the output's positive. So there's got to be a 0 in between these two. So the polynomial has a 0. I was using that intermediate value theorem, right, because polynomials are continuous. The polynomial has a 0 between x equals negative 1 and x equals positive 1. Now, I say a0. There could be more than one 0 in between negative 1 and positive 1. Also, it doesn't mean that the 0 has to be rational. You know, the 0 could be 1 over the square root of 2, 0.707 something. Right? So just because I can see that it has a 0 doesn't mean it's going to be rational. But because I noticed that, I'll start plugging in numbers from my list that are between negative 1 and 1. So now I'll go to some fractions. Like how about a third? This is between negative 1 and 1. See if this works. So 3 drops. This is 1 minus 1, that's 0. Then 0 minus 11, negative 11. And then negative 11 thirds minus 6, which is 18 thirds. Negative 11 thirds minus 18 thirds would be negative 29 thirds. Okay. And for the same with the same reasoning, I got a positive output at negative 1, a negative output at positive 1/3. So now I know there's a 0 between negative 1 and a third. Right? So I'll plug in, let's see, negative 1/3. That's between those. Drop the 3. Negative 1, minus 1 is negative 2. Then positive 2/3, minus 33 thirds minus 11. So positive 2/3 minus 33 thirds be negative 31 thirds. So I don't think this is going to work. This is positive 31 ninths, minus 54 ninths. 6 is 54 ninths. 31 minus 54, that's negative 23 ninths. But again, when I plugged in negative 1, I got a positive output. When I plug in negative 1/3, I got a negative output. So now I know that there's got to be a 0 between negative 1 and negative 1/3, which so now that leads me to checking negative 2/3. That's a number between negative 1 and negative 1/3, and again taking from my list only. So you got this negative 2 minus 1 is negative 3, and positive 2 minus 11, negative 9. Then positive 6 minus 6, 0. Fantastic. So I'm hoping you followed me there. Now, if you didn't follow me, you could have just brute forced your way through the entire list, and you would have eventually found that negative 2/3 is a 0. Okay. So now I can use this line here to factor the polynomial. So instead of 3x cubed minus x squared minus 11x minus 6, I can rewrite it this way as x plus 2/3 times, and then 3x squared minus 3x minus 9. Now if you don't like the fraction here, notice you can pull out a factor of 3, take the 3 from here and put it in here, factor a 3 out of this factor, right? All these are coefficients are a multiple of 3, and put it in the other one. When you multiply the other factor by 3, you'd have 3x plus 2, right, which has a 0 of negative 2/3. And then pulling a 3 out of this, we have x squared minus 1x minus 3. Right? These are the same thing. I just pulled 3 out of one factor, put it in the other one. I hope you can see that. All right, so now I'm down to pretty much what I want when I'm working with these degree 3s. We have a linear factor, which I know the zero of. It's negative 2/3. And now I have this quadratic factor. Let's find the zeros of this quadratic factor now. Now, unfortunately, this one is not factorable over the integers. It's not factorable over the integers, where all the coefficients are still integers. You know, factors of negative 3 that add up to negative 1 don't exist in the integers. So I'm going to be using the quadratic formula here to find the zeros of this factor. So we have x equals, right, so the zeros here are x equals, the opposite of the linear coefficient, opposite of b, which is positive 1, plus or minus the square root of b squared would be negative 1 squared, and then 4ac is 4 times 1 times negative 3 is negative 12, but then you're subtracting that, so it'll be positive 12. There's minus 4ac, and all that divided by 2a, which is just 2. So here are some zeros, right? So I now have all the zeros of this function, all the solutions of this equation. X equals negative 2/3, right? We saw that earlier. That's rational, right? This is a rational real zero, right? Rational numbers are real. And then we have x equals 1 plus the square root of 13, all divided by 2. This is irrational. Right? Square root of 13 is not a rational number, but it is real. Right? They're still real. There's no imaginaries here. And the other one's, 1 minus the square root of 13, all divided by 2. Still real, though. Right? It's irrational, but all these are still real numbers. Right? So the graph has 3 real, this polynomial has 3 real zeros, meaning that the graph of it will cross the x-axis 3 times at these 3 places. And let's see that. Right? Let's see that. So I'm going to go back and plot the graph of this polynomial, right? Polynomial function here. So the polynomial function is 3x cubed minus x squared minus 11x minus 6. Right, you see the 3x intercepts, 3 real zeros. So one of them is at negative 2/3, right? That's the rational one, negative 0.667. That's negative 2/3, right? If I plot the point, negative 2/3, comma 0, that's where that point will show up, see? Then the other intercepts, right, are at, let's label that. The other intercepts are at, negative 1.303 and 2.303. Well, those are rounded. Let me plot those points. Right, we said one of them was at negative 1 plus the square root of 13, all divided by 2, comma 0. Right, there's that point. All right, see it's on the graph. That's that 2.303. And then the other one, I'll just copy and paste this here and change the plus to a minus. 1 minus the square root of 13 over 2, comma 0. That's this green point here, the negative 1.303. Again, they're rounding to 3 decimal places for all these. But yeah, so our intercepts, our zeros are correct. These 3 real zeros of negative 2/3, 1 plus the square root of 13, all divided by 2, and 1 minus the square root of 13, all divided by 2. All right. Great. So let's just keep doing this. I just got a few more of these, actually 4 more. So another degree 3 polynomial. Once again, the coefficients of the polynomial are all integers, and we're finding the zeros, right? Where is this equal to 0? So by the rational zeros theorem, any rational zero this might have would have some factor of 3 in the numerator, so either plus or minus 1 or positive or negative 3, and have some factor of 2 in the denominator, so either 1 or 2. All right, so the list of possible rational zeros that I'm going to check are positive or negative 1, positive or negative 1/2, positive or negative 3, and positive or negative 3/2, right, 1.5. So just 8 numbers to check. And again, I might not even need to check all 8. So now we check numbers from that list, using synthetic division. So 2x cubed, negative 3x squared, positive 4x, positive 3 for the constant term. I'll check 1, drop the 2. 2 minus 3 is negative 1. Negative 1 plus 4 is 3. And then 3 plus 3 is 6, right? So no on that. But I do have a positive output. That's something to keep in mind. How about negative 1? Negative 2 plus negative 3 is negative 5. Positive 5 plus 4 is 9. And then negative 9 plus 3 is negative 6. So just like the last example, I'm noticing when I plug in 1, I get a positive. When I plug in negative 1, I get a negative. And being a continuous function, right, a polynomial function, by the intermediate value theorem, there's got to be a 0, at least one 0, between x equals 1 and x equals negative 1. Now, that 0 or those zeros may be rational or not, but all I have to work with are the rationals, so I might as well check them. Alright, so I'm going to go to numbers. The only numbers I have in my list that are between 1 and negative 1 are these half, and negative half. So I'm going to go to half. Plug in a half. So drop the 2. That's 1 minus 3 is negative 2. Then negative 1 plus 4 is positive 3. And then 3/2 plus 6/2 is 9/2, 4.5. Right. But again, I notice, hey, there's a negative output at negative 1, positive output at positive 1/2, so something between negative 1 and positive 1/2 should give me should be a 0, this function. Again, it might not be rational, but we'll see. I'll plug in negative 1/2 next. So negative 1 plus negative 3 is negative 4. Positive 2 plus 4 is 6. And then negative 3 plus 3 is 0. Hooray. So negative 1/2 is a 0 of this function. Negative 1/2 is a solution of this equation. And now I can use this, to factor the polynomial. It's x plus a half times 2x squared minus 4x plus 6. And then once again, I'm going to borrow a factor here. All these coefficients in the quadratic factor are a multiple of 2. I'm going to pull out a 2 from that factor and put it in the other one. So this other one, when I multiply by 2, would be 2x plus 1 times, and then when I factor a 2 out of this, we have x squared minus 2x plus 3. And once again, I have a quadratic factor, x squared minus 2x plus 3, that is not factorable over the integers. There are no factors of 3 that would add up to negative 2. So I'm going to use the quadratic formula here. We can find the zeros of this, right? The zeros of this would be x equals 2 plus or minus the square root of 4 minus 12, right? B squared minus 4ac would be 12, and then all that divided by 2a. So this is 2 plus or minus, remember this is the square root of negative 8, which is 2 times the square root of 2 times I. That's imaginary. Right? I times the square root of 8, but the square root of 8 simplifies to 2 root 2. And then all this divided by 2. So the zeros, right, the zeros of this function, the solutions of this equation, one of them is x equals negative half, which is rational and real, right? Rational, real. Every rational number is real. But the other ones are, dividing these by 2 here, you get 1 plus the square root of 2 times I. that's complex with an imaginary part. Complex with a non-zero, I'll just say complex with imaginary, right? So that's not real, right? It's not real. They're only asking us for the real solutions. And the other one's 1 minus the square root of 2 times I, same thing. So the only one that they want is this one, right? Negative 1/2. That's the only real zero of that function, the only real solution. The other solutions have an imaginary number in them. So when I go to graph this, the graph will only cross the x-axis at negative 1/2. Remember, the x-axis is a real number line, no imaginaries. And let's see that. All right, so again, the polynomial in this equation, the polynomial function we're finding the zeros of is, y equals 2x cubed minus 3x squared plus 4x plus 3. And do you see how it's only crossing the x-axis at one point? And that's at negative 1/2. There's only the one real zero at negative 1/2. Right, that means the other two, right? Because whatever the degree is, and we'll see this in future videos as well, whatever the degree is, that's how many complex zeros it will have, including the imaginary ones. Right, so we got negative 1/2, the only real one, right? That's the only place where it's actually crossing the x-axis, and then these two complex zeros with an imaginary part. Great. Right. So keep it going. Doing this again. So once now, ooh, a little different. Degree 4. So this, the higher the degree, just means the more repetitive it gets. You just do the same stuff over and over again. Like for the last 6 examples, I went from a degree 3 down to a degree 1 and a degree 2. And then we could find all the zeros. Here I have a degree 4. So once I find a zero, I'm going to factor it to a degree 1 and a degree 3. And then I just start over with that degree 3 like the previous, and I work with that degree 3 like the previous 6 examples. So it's just a little more tedious, that's all. But you're doing the same stuff again. All right, so we're finding the zeros of this polynomial, equals 0. And all the coefficients are integers, right? So I can apply the rational zeros theorem. Now I can just jump right to the list because look, the numerator's got to be some factor of 8, and the denominator is going to be 1. Right? So only the only possible rational zeros of this function, this polynomial, are the factors of 8. So positive or negative 1, positive or negative 2, positive or negative 4, and positive or negative 8. Right? So just these numbers here are the only possible rational zeros. And I can see that 1 works. Well, let's check them. Nice thing is that x equals 1 works here. Watch. 1x to the 4th, 2x cubed, negative 9x squared, negative 2x to the 1st, and positive 8. When I plug in 1, watch, you drop the 1. 1 plus 2 is 3. 3 plus negative 9 is negative 6. Negative 6 plus negative 2 is negative 8. And then negative 8 plus 8 is 0. So, lucky us. Worked out right away. So I can factor this polynomial, let's bring this over here, to instead of x to the 4th plus 2x cubed minus 9x squared minus 2x plus 8, instead of all that, we can use this line here and say, oh, 1 is a 0, so x minus 1 is a factor. And then these numbers here, the 1, 3, negative 6, negative 8, these are the factors of a degree 3. Right, this would be 1, so times 1x cubed plus 3x squared minus 6x and then minus 8. And now we're going to find the zeros of this degree 3 polynomial. And it's going to be the same way same as in the first 6 examples. I'll just say same as in previous examples. Right. So, make a list of possible rational zeros. Well, it'll be factors of -8 divided by factors of 1. So, same list. Same list. Right. Now you can keep going with this here, or just start it again. Right. So I'm starting again with this polynomial with 1x cubed, 3x squared, -6x to the first, and -8. And I'm using the same list, so I'll check +1 again. Zeros can have multiplicities higher than 1. Right. So just because something was a 0 earlier, it doesn't mean it can't be a 0 again. Right? You can have higher multiplicities, the same factor twice, 3 times, 4 times, right? So keep checking the same stuff if you need to. So drop the 1. 1 plus 3 is 4. 4 plus -6 is -2. And then -2 plus -8 is -10. So so 1 is not a 0 again. Right? It doesn't have its multiplicity is 1. So you're just going to see x minus 1 to the first power. You're not going to see another x minus 1. All right, then how about -1? Drop the 1. You got -1 plus 3 is 2. Then -2 minus 6 is -8. And then +8 plus 8 is 0. Hooray. All right. So now I can go even further. We have the x minus 1 from earlier. And now this degree 3 polynomial can factor using this line. Right? -1 is 0. So x plus 1 is a factor. And then we have these numbers here, which are going to be the coefficients of a quadratic. 1x squared plus 2x minus 8. And now I'm finding the zeros of this, which you can use the quadratic formula for, or try factoring. This one's actually factorable. Right? So we have finally x minus 1 times x plus 1, and x squared plus 2x minus 8 factors to x plus 4 times x minus 2. So nice linear factors. I can easily state all the zeros now, all the solutions of that equation that we started with. We have x equals 1, right? X equals -1, and -4 and +2. And there you have it. And those are all real, right? They're all rational. Right? Notice they're all rational, and they're on this list. They should be, right, if they're rational zeros. None of them are irrational. None of them have an imaginary number in them. Right? So they're all real. So that means if I were to graph this degree 4 polynomial function, it's going to cross the x-axis or touch the x-axis at all 4 of these values. And let's see that. Let's just double check. Make sure I did things correctly. So we have our polynomial as x to the 4th plus 2x cubed minus 9x squared minus 2x plus 8. All right, and look, see the 4 intercepts? There's that -4. That was one of them that I wrote down. -1, that was another one. +1, that was another one. And then +2. The exact same 4 intercepts, 4 zeros I have on my paper here. Excellent. Yeah, so again, just the higher degree, it's just you just start over again, right? Once you find a 0, you factor and you start again. You start again with that degree 3. And if it was a degree 5 polynomial, you just do everything more than twice. You do it 3 times until your eventual goal is to get down to degree 1 and degree 2 factors, because once you're down to degree 1s and 2s, finding the zeros should be easy. All right, so I got another one here. That's a degree 4 polynomial. And once again, all the coefficients of it are integers. We're trying to find the zeros, right? Where is it equal to 0? So it's all the same. All right, so by that rational zeros theorem, any rational zero, this is going to have, the numerator's got to be positive or negative 1, positive or negative 2, positive or negative 3, positive or negative 4, 6, and 12, right? All the factors of negative 12. Those are the possible numerators of any rational zero this polynomial might have. Right, and then the denominator's got to be either 1 or 2, right? Lead coefficient, factors of the lead coefficient. So the list that I'm going to be checking from, right, the list of possible rational zeros. You got positive or negative 1, positive or negative 1/2, positive or negative 2, and then 2 halves is 1 again, so I don't need to write that. Positive or negative 3, positive or negative 3 halves, positive or negative 4. Don't need to write 4 halves because I got 2 already. Positive or negative 6, 6 halves is 3, and then positive or negative 12, 12 halves is 6, right? So there we go. A lot of numbers to check. Right. Might not need to do all of them, right? But we'll find out, right? So now we check them. Again, using synthetic division. So 2x to the fourth, negative 3x cubed, negative 15x squared, positive 32x to the first, and then negative 12. Check 1, 2, 2 minus 3 is negative 1, negative 1 minus 15 is negative 16, negative 16 plus 32 is positive 16, and then 16 minus 12 is 4, right? So not 1. Try negative 1. Negative 2 minus 3 is negative 5, positive 5 minus 15 is negative 10, positive 10 minus 32, or plus 32, oops, negative 2, negative 5, positive 5, negative 10, positive 10 plus 32 is 42, and then negative 42 minus 12, negative 54. Alright, so like before, I'm seeing, hey, there's a positive output at 1, a negative output at negative 1, so I'll check some numbers between negative 1 and positive 1, see if I get a 0, because I got a positive and a negative. Now, there's got to be a 0, there's got to be at least a 0 between 1 and negative 1. Now, if that 0 is rational or not, I don't know, right? We'll find out. So I'm going to go to the only numbers between 1 and negative 1 are the halves here, right? So I'm going to go positive 1/2. That's 1 minus 3 is negative 2. Then negative 1 minus 15 is negative 16. Negative 8 plus 32 is 24. And then positive 12 minus 12 is 0. Fantastic. Fantastic. Okay, so we can factor this to x minus 1/2 times 2x cubed minus 2x squared minus 16x plus 24. And then you may have noticed that anytime a fraction is a 0, the coefficients of the quotient are all all have a common factor. These all have a common factor of 2. So I'm going to pull the 2 out of this and put it into this and make this 2x minus 1. And then if I factor 2 out of this quotient here, we have x cubed minus x squared minus 8x plus 12, right? That's factoring 2 out of all those. And now I'm starting over, right? Let's find the zeros of this degree 3. All right, so all the coefficients of this degree 3 are integers, so the list of possible rational zeros, right, again, we're using the rational zeros theorem here, would just be the factors of 12. Just the factors of 12, right? The lead coefficient's 1 here. So just plus or minus 1, plus or minus 2, oops, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. All right, those are all the ones I need to check now for this degree 3. All right, so I'm going to start over again with the synthetic division with the degree 3. So 1x cubed, negative 1x squared, negative 8x, and positive 12. Now here's the nice thing. If a number wasn't a 0 earlier, it's not going to be a 0 now. Because if it's a 0 now, if 1 was a 0 of this polynomial, it would have been a 0 of the original one too, because this is a factor. So I don't need to look at 1 and negative 1 again, right? So if a number wasn't a 0 earlier, it's not going to be a 0 now. So that cuts down my list, which is nice. All right, so now I just got these other integers to check. So how about 2? All right, so positive 2. And drop the 1. 2 minus 1 is 1. 2 minus 8 is negative 6. And then, hey, negative 12 plus 12 is 0. Fantastic. What luck. So now we have 2x minus 1 from earlier. All right, that still didn't go away. And then this x cubed minus x squared minus 8x plus 12 factors to, 2 is a 0. So x minus 2. And then these numbers here were for degree 2. X squared plus x minus 6. And then we start over again. Now you don't have to do the rational zero theorem anymore. But I am trying to find the zeros now of this degree 2 polynomial. Which, you can use the quadratic formula or try factoring. And this one is factorable. 2x, so we have 2x minus 1 times x minus 2. And then this factors to x plus 3 times x minus 2. So you see x minus 2 twice. So we have 2x minus 1 times x minus 2 squared, and then times x plus 3. Alright, so there's the polynomial completely factored. And we can state the zeros. Alright, the zeros are, 1/2. We saw that earlier. X equals 1/2. X equals 2 twice. Right, x equals 2 twice has a multiplicity of 2. And x equals negative 3, right, makes this last factor 0. Right, and again, I'll point that out. This one has, they would call this a double 0, right, or a repeated 0, because it has a multiplicity of 2. And you may recall from earlier videos, earlier parts of this chapter, when a real 0 has a multiplicity of 2, the graph is going to bounce off the x-axis at that 0. The other ones have a multiplicity of 1. The graph is just going to cross over the x-axis. But at x equals 2, we're going to see the graph bounce off, touch the x-axis and bounce off. And let's see that. All right, I'm going to actually go back to that Desmos site again and enter the polynomial we were given. I got a nice degree 4 here. We have y equals 2x to the 4th minus 3x cubed minus 15x squared plus 32x minus 12. And look at that, see x equals negative 3, it crosses over, has a multiplicity of 1. X equals 1/2, right, positive 1/2, that was another one, crosses over. And then x equals 2, you see it touches the x-axis, then bounces off. It has a multiplicity of 2, an even multiplicity. So it has everything I expected it to have, and everything we wrote down here. All right, fantastic. I've got just one more example. So we're going back to a degree 3 and doing the same stuff. Right, nothing's really changing. Only I think this one, the list of possible rational zeros is just going to have a lot more fractions. Right. So again, the polynomial we're looking at has all integer coefficients, so I can apply the rational zeros theorem. We're trying to find out where it's equal to 0, right? Finding the zeros of this polynomial function. So by the rational zeros theorem, I'll just make the list right now, hoping you can see it, right? The numerator is going to be positive or negative 1, and the denominator has got to be some factor of 4, so 1, 2, or 4. So we got positive or negative 1, positive or negative 1/2, positive or negative 1/4, and that's it. So if this has any rational solutions, any rational zeros, it's got to be one of these 6 numbers, right, or on this list of 6 numbers here. All right, and then we start checking them. Now I can already tell that -1's going to work. This would be -4 plus 3, be -1 plus 1 is 0. So I'm just going to punch that in right now. We have 4x cubed. Now, we haven't seen one of these yet, but don't forget to put zeros for the coefficient of missing powers as you descend. 4x cubed, 0x squared, then -3x to the first, and then your constant's +1. I'm just going to put negative. It's because I see it already. All right, if you see it already, use it. Drop the 4, then -4 plus 0 is -4, and then +4, -3 is 1. And then -1 plus 1 is 0. Right? So this polynomial factors to x plus 1 times 4x squared minus 4x plus 1. And this is nice and factorable as well. This is actually one of them perfect square trinomials. This is x plus 1 times 2x minus 1 squared. All right, that would factor to 2x minus 1 times 2x minus 1. So I can easily state the zeros now. Right? The zeros are x equals -1, and that has a multiplicity of 1. Right? There's only one factor, x plus 1. And then 2x minus 1, what makes that 0 would be +1/2. But again, that's a double zero, a double root. Has a multiplicity of 2, right? There are 2 factors. A double root, a double zero. Right? And there we go. And these are all real, right? All these are real numbers. So the graph will touch the x-axis at these values, but it's going to cross at -1, but bounce off at 1/2. And let's see that. All right, just one last example here. We have 4x cubed minus 3x plus 1 not equals 0. And then see at -1 it crosses over. At +1/2 it bounces off. Has a multiplicity of 2, even multiplicity, as I stated on paper. Alright, so same thing every time here. And you're given a polynomial with integer coefficients. You should be able to make a list of possible rational zeros. And then you start going through that list, checking them. Now you can check them with a calculator, synthetic division, right? But if you're doing it, if you're strictly asked to do it by hand, though, use synthetic division. And then once you find a 0, you can factor the polynomial. X minus that number times whatever the quotient is, and then you look at the quotient and start over. Try to find the zeros of that polynomial, and you keep going down, till you find all the zeros. And I'm hoping watching me go through these 9 examples here help you in some way, when you're trying to find the zeros of a polynomial function yourself. All right, and thank you very much for watching.